My bad.
Now we good now?
Yeah.
Okay, fantastic. Thanks for catching that. Okay, so there are certain questions that are really big ideas that you kind of need to understand. So one of these is problem number 7, okay? And it's this whole idea of electron volts versus joules, and electron volts is a measure of energy, so that's one of the things we're going to talk about. So on number 7, here's the story. So you've got a proton, just has a certain positive charge. We all know what that is, 1.6 times 10 to the minus 17th coulomb. Same thing with proton, electron doesn't make any difference. And you're told that it's been accelerated from rest through a potential difference of negative 1,000 volts. So your delta V is negative 1,000 volts. So it doesn't make any difference like what the voltages are in terms of the difference, okay? So because of the fact that this is negative 1,000, you could have started at 0 volts and ended up at 1,000 volts. Okay? What could have been your difference? 1,000, 0 and 1,000. Okay? So if it is a negative 1,000 volts in terms of a proton, so because it's delta V, which is voltage final minus voltage initial, so this would have been your V naught value, this would have been 0. So it doesn't make any difference. This could be 1,000 and 0. This could have been 2,000 and 1,000. The delta V, change in voltage, doesn't matter in terms of what the voltages are. It's just your change in voltage. Now, on 7a, it asks for what's the kinetic energy in electron volts. Okay, so on your sheet, you have this handy conversion back here that says 1 electron volt is 1.60 times 10 to the negative 19th joule. So 1 electron volt is 1.60 times 10 to the negative 19th joule, which conveniently also happens to be the charge on an electron or proton, okay? And so that's why it has the numeric value that it does. So 1 electron volts are just a measure of energy. So typically when you're dealing with values that are really small, like 1.6 times 10 to the negative 19, a lot of times we express that in electron volts, okay? It's a handy conversion to have, especially when you're dealing with very small quantities of energy like what you find with electrons and protons. So by definition, an electron volt, 1 electron volt, is the energy that it takes to take a single electron or proton and move it across a voltage difference of 1. So that's why 1 electron volt has the value that it does. So your answer to 7a, what is the kinetic energy in electron volts? You know what the delta V is. Oh, that's 1,000. So since that's 1,000, then there's no conversion to do. So on 7a, your kinetic energy is just 1,000 electron volts because it's just a single proton, right? That's the number. Now, if it was 2 protons, it wouldn't be that. It would be 2,000. But if that's just 1,000, it's just 1,000 electron volts. That's it. Boom, because it's a single proton. Now, the reason that isn't negative is because on 7a it's asking for the kinetic energy. Kinetic energy is a scalar quantity because it doesn't have a direction. So don't say, oh, that kinetic energy is negative 1,000. It's just 1,000. That's it. Now, when you get to B, what's the kinetic energy in joules? Oh, okay. So on B, the kinetic energy is joules. Well, you know that 1 electron volt is 1.6 times 10 to the negative 19th joules. So, you have 1,000 electron volts. 1 electron volt is 1.6 times 10 to the negative 19 joules multiplied across. You get 1.60 times 10 to the negative 16 joules, which isn't very much. This is why you work in electron volts, because it saves you the hassle of messing around with all the negatives, exponents, and things like that, because it's typically a small value. Now, on C, it says what is its speed? Now, when you get to C, here's the deal. At this point, you know what the kinetic energy is. You also know that kinetic energy equals 1/2 mv squared. Okay? Now, here's the interesting thing about this on a comparison. If this had been an electron, up to this point, every answer would be the same if it had been an electron, because an electron and a proton have the exact same charge. So if this had been an electron or proton, it wouldn't have made any difference. Up to this point, every answer would have been the same because the value of charge is the same. Now, here's the tricky part when you get to C. You want to figure out how fast it's going. Well, since you know kinetic energy equals 1/2 mv squared, and now you know what the kinetic energy is, oh, all right, 2 times my kinetic energy divided by the mass, the square root of that gives me that velocity. The velocities are not going to be the same, but the kinetic energies will be the same. So, which one has more mass, proton or electron? Proton. By a factor of about 1,800, okay? Protons are about 1,800 times more massive than the chihuahuas are, because the St. Bernards are big, massive, lumpy things that hang out in the nucleus. So, dude, chihuahuas, very small. So, for a St. Bernard, visualize this. So, you have a St. Bernard, right? Rough. And then you have this small little chihuahua. If they're going to have the same kinetic energy, what do you know about the chihuahua? Yes, the chihuahua has to be moving much faster than the St. Bernard does to have the same kinetic energy. Okay? Makes sense. Cool. Okay. Now, when you get to question number 8, or problem number 8, this one's a little bit tough. Okay? And that's why it has like all those bars beside it. So what potential difference is needed to accelerate a helium plus ion from rest to a speed of 1 times 10 to the 6 meters per second? Now, there's a couple of things that are going to play into this. First off, you have a helium nucleus, written like this. Okay? What does the top number represent? Mass number or atomic number? Mass number, which is the total number of St. Bernards and sheepdog. It's technically what you call the number of nucleons. So this has 2 protons and 2 neutrons. But it also has 2 protons, because remember, the bottom number is the number of protons. So in the nucleus, you got 2 protons and you've got 2 neutrons. That's how you figure that out. Now, it has a charge of 1 plus. This is not technically an alpha particle. An alpha particle actually has a charge of 2 plus because of the fact that it's lost both electrons. So that's what Rutherford did when he shot them at the gold foil. Rutherford actually shot alpha particles where both electrons had been kicked off. It comes out of a radioactive decay process, which we'll talk about later. But here's the point of this story. This has a charge of 1 plus. Now, when you look at accelerating particles across a voltage difference, that only works if they have a charged particle. Neutral atoms don't get accelerated across voltages because they have no overall charge. So that's going to be an important thing. So this only works because of the fact that we have stripped away a chihuahua from the helium nucleus. Now we have a charged particle. Now this thing can be accelerated across the voltage. Now, bigger idea. Let's say here's some positive charge. I don't care what it is, it's just a positive charge. Okay? So, if that's a positive charge, are the voltage lines going around it positive or negative? Positive. As you go away, what happens to the value of the voltage lines? They go down, because voltage equals KQ overall, right? So this might be 100 volts, this might be 50 volts, that type of thing. Now, this is going to be important in terms of which direction these things are going to move. So if you look on number 8, we're going to accelerate this proton from rest to a speed of 1.0 times 10 to the 6th meters per second. So imagine I'm going to give you this proton, which would be really, really tough to do, but stay with me here. I'm going to give you a single proton, and I want you to accelerate from rest up to 1.0 times 10 to the 6th meters per second. From rest. Now, here's the question. Would you want to put it close to the nucleus and have it go away, or would you want it further away here and have it move to the nucleus?
The proton?
The proton.
Closer.
Closer. Why?
Because it'll
It'll repel, right? It's going to get further away. So, if you look at this, this is going to be important. In this situation, if it's being a proton, you need to go from high positive voltage down to low positive voltage. Okay? It's like you're rolling downhill. It's going to gain speed. Now, if this was an electron, what would you want to have happen? You're going to have it way out here, and it's going to move in because it's going to become attracted to it. Okay? So, if you determine what's going to happen with us going from high to low, you have to look at two things. What's the voltage in the field, and what's the charge of the particle in the field? Because that's going to drive which direction this thing's going to go. Okay. Now, if you look at number 8, you're going to go from 0 to 1.0 times 10 to the 6th meters per second. Is work going to be done on the proton?
Yes.
Absolutely. Why?
Force over distance.
How do you know?
There's a force over that, and then it's going over.
Okay? But just because you exert a force over a distance, okay, right? Does that necessarily mean it's going to speed up?
No.
Well, it could also slow down. In this case, we want it to speed up. So, work's going to be done because a couple of things. We're going to exert a force over distance. Is the kinetic energy going to change?
Yes.
Yes. Kinetic energy is going to change. And it's also, that charge has to work through a difference in voltages. Okay? Now, knowing this, the mass and the velocity, could you calculate the kinetic energy? Yeah. Oh, okay. We can do this. Kinetic energy equals 1/2 mv squared. Okay? Now, the mass gets a little bit tricky. Okay? So, on the back, on this sheet, it's got a proton mass and a neutron mass. Notice that those are the same value. Okay? Once we get into nuclear reactions and Einstein's equations of E equals mc squared, you'll actually see that they're not the same. Okay? You'll actually see that those masses are a little bit different. Don't worry about it for now. Okay? Do not worry about it for now. Just let them be the same. So when you do the mass calculation, you've got to take into account that you have 2 protons and 2 neutrons in that nucleus. So that mass needs to be 4 times 1.67 times 10 to the negative 27 kilograms. Okay? Just don't use 1 proton. You got to use the 4 nucleons that are in that nucleus. And then you've got your 1/2, and then you've got your speed, 1.0 times 10 to the 6 meters per second squared.
This is for him.
And to save you some hassle, you get 3.34 times 10 to the negative 15 joules. Okay? So if you crunch all the numbers, that's what you're going to get. So, at this point, can we calculate the work that's done?
Yeah. We have to change in kinetic energy.
Yeah, so if you have the change in the kinetic energy, you also have the work.
Wait a minute.
Because what's the initial kinetic energy? Zero.
Oh.
Oh, right? So my initial kinetic energy is 0. There's my final kinetic energy, right? So remember, work equals change in some type of energy. Is my change in energy a positive value or a negative value?
Positive.
Because I'm speeding this thing up. Cool. Okay. Now, the next thing it wants to know was what's the change in voltage. Now, this work is change in E. So, in this situation, not only do you have the change in that value, you also know the change in the OOE. Because it's a charged particle, the OOE changed. We did work. We changed the value of OOE. And we know that because OOE equals KQ1 Q2 over R. We have changed the distance between these charged particles. Okay? So therefore, we know what the OOE is. So here's the whole point of this. You know that OOE, if you look here, okay, there's variations on OOE. OOE equals Q delta V. So we just found the change in the electrical potential energy because it's a charged particle, and we know what this is. So now we have OOE. Now, the charge. Do we use the charge on the 2 protons, or do we use the fact that it's a singly charged ionized particle? Singly charged ionized particle. For this value of Q, because it's a singly charged particle, that's just 1.60 times 10 to the negative 19, like you've always used. So then your delta V, if you go through all of that, you get 2.1 times 10 to the 4th volts. Okay? So there's delta E. You know what the value of Q is. Find your voltage. That's the voltage necessary to make that happen. So what that means is that you would have to have a pretty strong high voltage system here, close to whatever creating that, to make it go and speed up. Now, how would the numbers change if it had been an electron? If I said, hey, I want to take an electron from 0 to 1.0 times 10 to the 6 meters per second. Okay? But I'm just going to do one single electron.
Mass is less.
Mass is way different.
Mass changes.
Mass less.
The
Mass equals less.
Mass equals less. Okay.
Tiny mass.
So instead of taking 4 times 1.67 times 10 to the negative 27 kilograms, you would just use the mass of one single electron, 9.11 times 10 to the negative 31st. So the mass in the kinetic energy equation is going to be much less. So therefore, the work is going to be much less. Okay? Because you're going to have less change in the kinetic energy. So, but you're still going to be dividing by the same Q because an electron and a positively charged helium ion have the exact same value of charge. It's just a different value in terms of size. So, since your delta V would be smaller, your voltage would be smaller. It wouldn't take as much voltage to accelerate that electron as it would that helium nucleus. Okay, now that leads to problem number 9. An electron with an initial speed of 5,000 is brought to rest by an electric field. So, one of the first things that you have to be able to answer on a question like this, and I swear to you there's going to be questions like this on the final, okay? So, you have an electron which has a negative charge, right? And you want to move it from 500,000 meters per second to brought to rest. Okay, let's talk about this. So, let's look at the big idea. So here's this electric field created by a negatively charged plate and a positively charged plate. Okay? Big idea. Don't even worry about the electron. You do not worry about it moving. You do not worry about anything. If all I said is that here's a negatively charged plate, there's a positively charged plate. That's all you know. And I ask you, what would be the direction of the electric field? Is it left to right, right to left? This should be something you should be able to do without any hesitation. Right to left?
Yeah.
Why?
There's positive.
Because the positive test charge would feel what? It would feel repulsed from the right, and it would feel
Attraction from the left.
attracted to the left. So the electric field would be going this direction, right?
Yes.
Cool with this. Got it. Now, if you were to draw voltage lines in between, okay? If you were to draw voltage lines in between, that wasn't loud.
What?
Okay. So here's my question. Let's compare line A, B, and C. Would lines A, B, and C, starting with A, first off, would they be positive voltage lines or negative voltage lines? Positive. Okay? Because of the fact you're close to a whole bunch of positive charges. As it goes across, what would happen to the value of the voltage lines? They would go down. So this might be like 200 volts, that might be 100 volts, that might be 150, right? So you go from 200, 150 to 100. Okay? Cool, right? Got that. Now, here's the next question. If you read this question, you have an electron moving at 500,000 meters per second. It's brought to rest by an electric field. So, where would we shoot the electron? Would we shoot the electron and have it go from the negative to the positive, or the positive to the negative? Why? Because it's going to be repelled by the negative and pulled back by the positive. So an electron, we would shoot going in this direction. Got that?
Yes.
Direction it's going to go. True?
Yes.
Okay. So on question A, it says, did the electron move into a region of higher potential or lower potential? It's going to go from high to low. So there was a whole bunch of things that you had to think through to get to that first answer. So now, if it was a proton that you were trying to stop, that would go from low to high. Because the proton, you would shoot from the negative across that way. So this is why you can't say, oh, to slow something down or speed something up, it's always low to high or always high to low. You have to look at, there's two things that you need to consider. Is it speeding up or slowing down? Is it an electron or a proton? Because they play out completely differently in terms of the voltage. So you can't always sit there and go, oh, I'll just remember it's always high to low. Well, no, it's not. Because it depends upon if you're speeding it up, if you're slowing it down, if it's an electron, or if it's a proton. That's what you have to think through. So don't just sit there and memorize it, oh, it's always high to low. No, it's going to be a train wreck when you begin to analyze this. Okay. Now, then you have B. It says, what's the potential difference that stopped the electron? Now, I want you to understand the difference between UI and voltage in terms of the terminology. So when you see potential difference means the same thing as voltage, okay? So potential difference and voltage mean the same thing, right? It's just how you want to express it. UI is just UI. Now, it might say, hey, what's the potential energy? But don't confuse, if they wanted you to talk about UI, they would have to say specifically, what is the potential energy as it moves across the voltage or something like that. But if it just says, what's the potential difference? Potential difference is a measure of voltage. Now, here's your bread and butter, okay? Is the kinetic energy of the electron going to change? Excuse me. Is the kinetic energy of the electron going to change?
Yes.
Yes.
Yes, because you're going from 500,000 meters per second to 0. So you can find the initial kinetic energy, right? Using 1/2 mv squared. You know how fast it's going. You know that it's an electron. Okay. You know its mass. Boom, you smash the numbers. So if you smash those numbers to save you some hassle, you get, where's it at? 1.14 times 10 to the negative 19th joules. Okay? So that's how much energy that has. Now, if I asked you, well, how many electron volts is that? What would you do?
Use divide by 1.6.
Yeah, go ahead and
Yeah.
divide by 1.6.
Yeah, so you know the conversion between electron volts and joules. So if I said, hey, what's the electron volts? You have that conversion. Okay? Now that you have that, you want to find the voltage. So here's your bread and butter. Delta U equals Q delta V. But this delta U is the change in any generic type of energy. In this case, this is a change in OUI. Okay? So once you get this, then you're going to know your value of delta U, because delta U is the same thing as work, which is this generic change in some type of energy. So you know that, you know the value of Q, solve for your change in voltage. Okay? So when you get to that one, you get negative 0.71 volts. Now, why would you need negative voltage?
Because the kinetic energy decreases, so the kinetic energy change is negative. So. Oh, okay.
You're going from high to low, right? Voltage, we said, had to go from high to low. So your delta V had to be a negative value. Now, then it says, what was the initial kinetic energy of the electron in electron volts? So there's a couple of ways you could do it. As you know, it's one electron. You could just say, oh, that's 0.71 electron volts. Okay? Because it's just one electron. Or you could take this and go through that conversion. Same thing. Okay? The exact same thing. All right. So let's see, we got that one. 14's a good one. So 14 now should make sense. So I'm just going to stop for a little bit. Can you stop that camera? I want you to try 14.